A machine learning model can be 99% accurate and still fail at the only thing it was supposed to do. Imagine a medical AI that looks at 1000 patients and proudly says, I got 99% of them right. Sounds impressive, right? But then you look closer and realize something terrifying. It missed every single sick patient. So was the model good, or was the accuracy score hiding the truth? That is exactly what we are going to unpack in this video. We will see why accuracy can be misleading, what the confusion matrix reveals, and how precision, recall, and F1 score help us understand what a model is really doing. Hi, welcome back to my channel, and if you're new here, welcome. My name is Anna, and on this channel I explore machine learning concepts in a simple and intuitive way. If you enjoy this kind of content, consider subscribing and feel free to leave a like and a comment so that more people can see this video. Today we are going to look at one of the most important ideas in model evaluation: why a high accuracy score doesn't always mean a good model. Let's start with a simple example. Imagine we have a dataset of 1000 patients. Out of these, 990 are healthy and only 10 actually have a disease. So the disease is very rare in this dataset. Now imagine we build a machine learning model, and this model is extremely simple. It simply predicts everyone is healthy. So for every single patient, the model says no disease. At first, it sounds like a terrible model, and honestly, it is. But now let's calculate the accuracy. There are 990 healthy patients, and the model correctly predicts all of them as healthy. So the model gets 990 predictions correct out of 1000. That gives us 990 divided by 1000, which is 99% accuracy. So according to accuracy, this model looks amazing. But here is the problem. There were 10 patients who actually had the disease, and the model missed all of them. So for the most important cases, the model completely failed. It detected 0 out of 10 sick patients. And this is the main problem with accuracy. Accuracy only asks how many predictions were correct overall, but it doesn't ask what kind of mistakes did the model make. And in many real-world problems, the type of mistake matters a lot. So to understand the model properly, we need a better tool, and that tool is called the confusion matrix. The confusion matrix is basically a table that shows us not just whether the model was right or wrong, but exactly how it was right or wrong. Let's draw it. On one side, we have the actual class, so what is true in reality, and on the other side, we have the predicted class, so what the model predicted. For a binary classification problem, we usually have two classes, positive and negative. For instance, in disease detection, positive means the patient has the disease. Negative means the patient doesn't have the disease. Now the confusion matrix has 4 parts. First, we have true positives. That means the model predicted positive, and the actual answer is also positive. So in our example, the model says the patient has the disease, and the patient really has the disease. That is a correct positive prediction. Second, we have true negatives. That means the model predicted negative, and the actual answer was also negative. So the model says the patient is healthy, and the patient really is healthy. That is also correct. But then we have 2 types of mistakes. The first mistake is a false positive. That means the model predicted positive, but the actual answer was negative. So the model says the patient has the disease, but actually the patient is healthy. This is like a false alarm. The second mistake is a false negative. That means the model predicted negative, but the actual answer was positive. So the model says the patient is healthy, but actually the patient has the disease. And in this example, this can be a very dangerous mistake because the model missed a sick patient. Here I want to also add that the confusion matrix is not only for 2 classes. If we classify cats, dogs, and birds, the confusion matrix becomes 3 by 3. If we have 10 classes, it becomes 10 by 10, but the idea stays the same. Now let's go back to our simple model. Remember, we had 1000 patients, 990 were healthy, 10 had the disease, and the model predicted that everyone was healthy. So how does the confusion matrix look? The model correctly predicted 990 healthy patients as healthy, so we have 990 true negatives, but the model missed all 10 sick patients, so we have 10 false negatives. The model never predicted disease for anyone, so we have 0 true positives and 0 false positives. Now suddenly we see the problem much more clearly. Accuracy gives us one number, 99%, but the confusion matrix shows us the full story. The model is good at identifying healthy patients, but completely useless at finding sick patients. And this is why the confusion matrix is so important. It shows the types of correct predictions and the types of mistakes. Now let's define the metrics. The first one is accuracy. Accuracy is true positives plus true negatives divided by all predictions. So, in simple words, accuracy tells us out of all predictions how many were correct. And this is useful when the classes are balanced and when false positives and false negatives have similar costs. But as we saw, when the dataset is imbalanced, accuracy can be misleading because the model can get a high accuracy just by predicting the majority class. So we need other metrics. The next metric is precision. Precision is true positives divided by true positives plus false positives. But instead of memorizing the formula, it's better to understand the question precision is answering. Precision asks, when the model predicts positive, how often is it correct? So precision is about trust. For instance, imagine we have a spam detection model. If the model says an email is spam, we want to know, how much can we trust that prediction? If precision is high, then when the model says spam, it's usually right. If precision is low, then the model creates many false alarms. So in spam detection, low precision could be annoying because important emails might be incorrectly sent to the spam folder. So precision is very important when false positives are costly. Now let's talk about recall. Recall is true positives divided by true positives plus false negatives. So again, the formula is useful, but the question is more important. Recall asks, out of all actual positives, how many did the model find? So recall is about catching positive cases. In our disease example, recall is extremely important because we want to know, out of all patients who actually have the disease, how many did the model detect? If recall is low, the model is missing many positive cases, and that means we have many false negatives. So recall is very important when false negatives are costly. For instance, in disease detection, fraud detection, or safety systems, missing a positive case can be much worse than creating a false alarm. So the difference between precision and recall is this. Precision asks, when the model says positive, is it usually right? Recall asks, did the model find most of the actual positives? Precision is about the quality of positive predictions. Recall is about the coverage of actual positives. And depending on the problem, you might care more about one than the other. For instance, in spam detection, you might want high precision because you don't want normal emails to be marked as spam. But in disease detection, you might want high recall because you don't want to miss sick patients. So there is no single best metric for every problem. The right metric depends on the cost of the mistake. Now, sometimes we care about both precision and recall, and that is where the F1 score is useful. The F1 score combines precision and recall into one number. The formula is, the important idea is that F1 score becomes high only when both precision and recall are reasonably high. If precision is very low, F1 will be low. If recall is very low, F1 will also be low. So F1 score is useful when we want a balance between precision and recall, especially for imbalanced datasets. But it's also important to remember, F1 score is not magic. It's just one way to combine precision and recall. In real projects, we should still think about what kind of mistake is more expensive. F1 score is useful when false positives and false negatives both matter, but it assumes precision and recall are equally important. Now let's move into the notebook and see this in code. The first question is, can a model really have 99% accuracy and still be useless? Here we create the simple dataset we saw in the animation with 1000 patients. 990 are healthy and only 10 actually have the disease. Then we create the simplest possible model. It predicts that everyone is healthy. When we calculate accuracy, we get 99%. At first, it looks amazing, but now look at this line. The model detected 0 sick patients. So this is the problem. Accuracy looks only at how many predictions were correct overall. It doesn't tell us which mistakes the model made. Now let's look at the confusion matrix. Here the rows show the actual class and the columns show what the model predicted. We can see that the model correctly classified 990 healthy patients, but it missed all 10 sick patients. So we have many true negatives but also 10 false negatives. And in medical problem, those false negatives are the dangerous part. This is why the confusion matrix is so useful. It shows the full story behind the accuracy score. Now let's calculate the metrics manually. Accuracy asks, out of all predictions, how many were correct? Precision asks, when the model predicts positive, how often is it right? Recall asks, out of all actual positives, how many did the model find? An F1 score tries to combine precision and recall into one number. In this example, precision and recall are equal to 0 because the model found none of the sick patients. So even though accuracy is 99%, the model completely fails at the most important task. Now let's compare a few models. The first model predicts everyone is healthy. It has high accuracy but 0 precision and recall. The second model predicts everyone has the disease. This catches all sick patients, so recall is high, but it creates many false alarms. The third model is more realistic. It catches some disease cases, but also makes some false positives. This comparison shows why we should not judge a model using only accuracy. Different models can make very different types of mistakes. Now let's add a simple cost to the mistakes. Here we say a false positive has a cost of 1, but a false negative has a cost of 100. This is not a universal rule, but it helps us understand something important. The highest accuracy model is not always the best model in the real world. Now let's move to a real dataset. Here we use the breast cancer dataset from scikit-learn. In this notebook, we define malignant as the positive class, because that is the serious case we want to detect. Before training a real model, we start with a baseline model. This model simply predicts the most common class. The baseline is important because it tells us what a lazy model can achieve without learning anything useful. Now we train a logistic regression model. This model performs much better than the baseline, but instead of only looking at accuracy, we look at precision, recall, F1 score, and the confusion matrix. This gives us a much better understanding of what the model is doing. We can see that all of those metrics are high, and from the confusion matrix, we can see that the model predicts correctly in most of the cases. Let's look at thresholds. Many models don't just predict positive or negative directly. They first output a probability. Then we choose a threshold. For instance, with a threshold of 0.5, the model predicts positive when the probability is at least 50%. But if we lower the threshold, the model becomes more sensitive. It predicts positive more often, which usually increases recall. If we raise the threshold, the model becomes more conservative. It predicts positive only when it's more confident, which can increase precision but may reduce recall. This is the precision recall trade-off, and this is why the best threshold depends on the problem. For disease screening, we may prefer high recall because we don't want to miss sick patients. For spam detection, we may prefer high precision because we don't want important emails to be marked as spam. Finally, let's answer one common question. Can precision and recall be used for more than 2 classes? Yes, here we use the iris dataset, which has 3 classes. The confusion matrix becomes 3 by 3 instead of 2 by 2, and the classification report gives precision, recall, and F1 score for each class. The idea is the same. For each class, we can ask how well the model identifies that class compared to the others. So the main takeaway from this notebook is accuracy is not enough. Always look at the confusion matrix. Then choose precision, recall, or F1 score depending on what kind of mistake matters more. Because in machine learning, the best metric is not the one that looks the the highest. The best metric is the one that matches the real-world problem. So how do we choose the right metric? Here is a simple way to think about it. If your classes are balanced and all mistakes have similar cost, accuracy can be reasonable. If false positives are expensive, focus on precision. For instance, if a model flags a transaction as fraud, but it is actually normal, that can block a real customer. If false negatives are expensive, focus on recall. For example, if a medical model misses a disease, that can be very serious. If you need a balance between precision and recall, use F1 score. And if you want to understand what is really happening, always look at the confusion matrix. Because the confusion matrix gives you the full picture. It shows not only how many predictions were correct, but also what types of mistakes the model made. And that is usually much more useful than one single number. So let's summarize. Accuracy tells us out of all predictions how many were correct. Precision tells us when the model predicts positive, how often is it right? Recall tells us out of all actual positives, how many did the model find? F1 score gives us a balance between precision and recall. And the confusion matrix shows us the full picture of correct predictions and mistakes. The most important takeaway is this: the best metric depends on the problem. In machine learning, we don't choose metrics randomly. We choose them based on the cost of different mistakes. So next time you see a model with very high accuracy, don't immediately assume it is good. Ask, is the data balanced? What are the false positives? What are the false negatives? And which mistake is more important? If you haven't seen my previous videos, I highly recommend checking them out. I cover topics like KNN, principal component analysis, and linear regression in a similar style. If you found this video helpful, feel free to like it and leave a comment. It really helps more curious minds like yours discover the channel. If you're interested in this kind of content, consider subscribing so you don't miss future videos. As always, all the resources, including the code, will be in the description below. Thanks for watching, and I will see you in the next one. Bye!